So hi everyone, here is Davide Schiavone and from Open Hardware Group. And the reason why I'm here is to talk to you about the Core 5 cores, the CVE4 and A6, as Rick introduced in the talk before, and their histories under the PULP project. My story with open hardware and open source hardware started exactly together with my PhD, where I started working under the PULP project. PULP is from 2013, and it's a joint project between the University of Bologna and ETHZ Zurich. The main purpose was, if you look at the market, if you see either high-performance microprocessors consuming a lot of power, or low-power microprocessors but lacking in performance. And the idea was having both performance and low power in a single chip. And how to do that? So the idea behind PULP is, okay, how can we combine these two features through near threshold computing, so using the supply voltage near the threshold of transistors, and parallelizing to recover the performance loss due to the low voltage supply. Here in the left side of the slide, you see how a PULP microcontroller looks like. If you see, is very CPU centric, which means that the main IPs here are microprocessors, and we decided to base our IPs on microprocessors, as we want to cover in the Internet of Things a broad set of algorithms, not just one. And so to do that, you want to program this in software for versatility reasons, and also for development of the IP cost. So you develop one processor, and that is good for most of your algorithms that you have in mind. We started in 2013 from OpenRISC, and we developed our Orion CPU. And it was very simple, 32-bit, 4 pipeline stages in order, one of the common architecture in the embedded system domain. And then we start customizing the ISA, adding DSP instructions, hardware loop, SIMD instructions, bit manipulation, load and stores with auto-incremental pointers. And this has been done to increase the performance of the processor, so that the algorithm that this IoT node was computing will have higher performance, but still in the low power budget range. And we start prototyping our microcontrollers with ST28 FDSOI technology, UNCL65, and so on. Then once RISC-V started around 2015, we started investigating this new ISA, because there was a lot of things going on around RISC-V. Okay, sorry. The live things. So we start using RISC-V as this new ISA was promising in terms of activities behind it, because it was easy to customize, actually designed for customization as well, which was one of the main reasons why we start customizing the OpenRISC core. And we developed our first RISC-V core based on RISC-V, starting from our old IP. And together with this, we started open sourcing our IPs. So as an academic project, we start pushing our work on GitHub under a very permissive license based on Apache 2. And together with the core, we started sharing also some other peripherals and interconnects, and we built a very simple microcontroller called Palpino that was used as a vehicle to use our core. Together with the core, we also published custom GCC that was using the custom instruction sets that we extend our core for. And we start participating to all the RISC-V workshop and to the open source activities behind it. This is how RISC-V looks like. It implements the integer multiplication complex instructions from RISC-V, eventually the floating and atomics, and the PULP extensions. It has a RISC-V debug compliant features, some minimal features for security, as PMP, user mode. The architecture has been kept as the original OpenRISC project. And in the Global Foundry 22 technology, can reach more than 600 megahertz. And as you see here in the left side of the slide, you see a little piece of assembly code where you are implementing a convolution kernel, which is one of the main pattern recognition algorithms one can want to run on the IoT nodes. And you see how the code size and the number of instructions and the cycles are way more efficient. That was the key reasons why we were using this core and these extensions. We start doing many SoC tape outs based on our PULP IPs. Now we are at 37, I guess 38 in the last week. Probably we have done another more, because we are a large group with 2 universities. We did 22, 28, 40, 55, 65, 110 for the analog mixed signals SoC, and really a lot of attention start orbiting this PULP idea also at university. But what we learned by doing these open source activities as well was we were seeing that the number of users of this RISC core and the other IPs were growing. Also, not only from an academic point of view, but also from industry side. For instance, MBCosm starts doing a very later simulator for RISC. Some other people start writing libraries for Palpino to use the custom extensions of the core. People were start using it, and so finding bugs, reporting it on GitHub, giving us solutions sometimes. And also they were started actually building something on top of these open source IPs. And not just toys. Here you see that actually Greenways is selling a wall pulp-based microcontroller called the GAP8, which is integrating 9 of those RISC cores. The Vega board is also was also giving a PCB with 2 of our IPs, Dolphin. Google, together with Valtrix, start using RISC to evaluate it for the Pixel Visual Core, and they showed actually in Barcelona during a RISC-V workshop their experience. And so there were a lot of questions for us, documentations, requirements, bugs, a lot of bugs that have been found during this process. And for us as a research group, verification, documentation, and details, let's put it in quotes, about some specs were less important, of course, than performance or other research purposes. So there was this gap between the two worlds. University wants to make research, and industries want to make products. Because of these questions and this attention behind these IPs, we start actually doing also PULP trainings, both to universities and companies. So we were flying over there and showing them, hey, these IPs works like this. This is the theory behind them. We were doing exercises with them to improve the learning process of the RISC course or PULP in general. Some ad hoc tutorials and Q&A sessions with them up to June 2018, where we actually did one generic training that has been recorded also on YouTube and now available on for everyone, which is more, a little bit more generic, but still, this all to make people more comfortable in using these IPs and also receiving feedbacks. And we were actually very happy to see that how the community around this course was growing. Up to the point that the number of questions, bugs, and verification needed by companies was overwhelming for a research group. And at that point, you start seeing that you actually need industrial support for your course if you want to build products on top of that. And in June 2018, the risky core moved to open hardware under the name of CVE32E40P specifically, under the CVE32E4 family of Core 5, and with the idea of being improved with bug fixes, RISC-V compliant features, verified specifically with all these instructions, and silicon proven. And the same happened also for the smaller version of the core, Zero Risky, that moved to low risk in UK, and to Ariane, that we will talk about later, that also moved to open hardware. As Rick mentioned, the open hardware work in technical groups, and specifically, I'm the director of the Cortas group, and Ariane and Jerome are the chair and vice chair respectively. The core kept the same permissive license, so it's truly open source and exactly like before, but now it's available to everyone at industrial level quality. So we are doing a lot of works in verifying the core, and I will be talking about all the improvements in a minute. But still with the same permissive license as before, still open source, all available on GitHub as before. And what we do on the Cortas group is deciding what are the priorities of the core and what are the tasks that have to be faced immediately, what can we do later, what are the features that are needed now, what should we change, etc., etc. This still works through GitHub with issues, questions, and pull requests for what concerns the technical work, whereas the decisions happen on Mattermost. As I said several times during this topic, the very first thing that was missing in the core was verification, because again, was not the priority of a research project under the university. And what we start doing is deciding how to change the core and the improvements we should do based on that. So let's say design driven by verification, if you want. It's not really like this, but at the point in time we were with Risky, we decided to say, okay, now most of the effort should be on verification. So let's decide the set of features that we want to verify, clean the code, and make it very let's make it easier to be verified, reducing the number of parameters that will reduce the number of configurations the verification has to verify, sorry for the job, and all these things. Let's look at them in detail. So first, we've done a little bit of style. So all the file names have been changing to be consistent. The code has been cleaned up, and as said, the parameters were reduced a lot. So at the beginning, for the integration of the core, you had many parameters. Now I don't recall how many, and that was making a little bit difficult for new users to integrate the core, because what shall I put here? What's the value here? What is standard and what's not? And we try to simplify this as much as possible, reorganize the files in different folders, and there was a little test bench inside the core that became the baseline for the Core 5 Verif project for verification, but that also has been simplified and just used as a simple example for running a simple hello world. We start adding assertions and all these things. we start improving the core to be more RISC-V compliant. So we actually changed the interrupt scheme together with ETHZ in my group to be compliant with Clean. Scilabs in OpenArdour, we did the performance counters that were custom and now RISC-V compliant. Many bug fixes to make the core compliant, specifically in the debug side. Scilabs has changed together with OpenArdour the interface and the bus protocols toward the memories, removing combinatorial path, increasing the frequency, increasing the quality of the transactions towards memories, and making it more AMBA friendly, which is standard for industries. The hardware loop logic has been redesigned to also be easier to be verified and with more restrictive specs. The instruction fetch changed. So these were the parts where, let's say, most of the bugs and have been found in the past, let's say. The PULP ISA extensions have been kept. They are the masterpiece. They were the masterpiece of RISC-V, and they are still available in OpenArdour, and they are under verification as well. So for those that were fan of the PULP ISA, they are still there. But now can be parameterized. So for those that don't need this, can remove them or simply not add them to their own IP to simplify verifications or improve the area of the core. Documentation is another big topic, as many questions were actually for the documentation. Where is this specified? Where is that specified? And as a research as a PhD student, most of the time I was replying, the RTL per se is the documentation, but actually this is not really the way that industry would like to deal with. So we actually rebuilt the whole documentation structure of RISC-V that was work-based, not updated, and very difficult to maintain. Now we actually have a text-based on HTML website available for everyone, up to date, and we take it as seriously as the RTL, nothing less. In a month, we are targeting the first RTL freeze, where most of the improvements come from the fact that now the core has been verified or it's under verification. Let's give us a month more. And so many bug fixes happen. If you are curious about the technical details, you can go on the GitHub page and see all the commits that have been done on the core, and you will see many of them. And the way we are working is verification team or any other member or user of the core find bugs in the documentation, RTL, or in the tracer, whatever. They report it to the design team, and we fix them, and again and again and again. This is in a loop to reach a very high quality IP, and this happens in a multi-member company way. So a guy from the company X verify the core, finds a bug that another person from the company Y fixes, and all these things is actually, for me at least, is a new experience, and I never seen such thing in place, and actually very, let's say, very entertaining experience with that, and many feedbacks and different people to agree with, and it's really a nice experience. In the future, we want to adding the FPU interface back, so verifying also the FPU, improving it, adding back securities, adding the optimization for the FPGA, and then many more. Sorry, I'm making. And going back to the other IPs of OpenArdour born under the PULP project is Ariane. And Ariane was born in 2016, so a little bit later than RISC-V. And the idea of Ariane was like, many applications are based on operating systems or libraries that work together with an operating system like Linux. And to do that, you need actually another kind of CPU, an application class CPU. And back in the days, there was no open source IP written with a standard language as Verilog, HDL, System Verilog. And so we developed our own and 64-bit version, general purpose with complex instructions, running Linux. And this is Ariane. As you see here, Ariane has a different architecture, six pipeline stages, with branch prediction, scoreboarding, and it reaches a way higher frequency, like 1.5 in 22 nanometer. As said, also Ariane moved to open hardware. There are contributions that are making the core configurable to have both the 64 and 32-bit versions. So that's why the name is CVA6 without the bit width in the name, as this is a parameter. And as soon as the members are ready, also Ariane will have the same activity that CVE32 had. So for instance, new documentation, the verification environment around that can leverage the existing one for the CVE32. At this moment in time, the 32-bit parameter is a pull request that is under the review, so that we can have also this new flavor of the core, and together with that, the FPGA optimizations. So I want to thank everyone for the attention, and this is a call to action, and we would like to have you to join us in the design team or verification team to help us to build these IPs and to make them even higher quality. There's a lot of things going on, a lot of activities on both the application class and embedded class processors. If you would like to be part of this unique experience, please contact us, either me or Rick or Florian, the other members of Open Hardware, and thanks a lot. Let's see if we have questions. Okay, so what features does PULP ISA extensions provide? On top of RISC-V based instructions, where can we get the detailed documentation of these PULP, I guess, ISA extensions? Okay, so all the extensions are documented in on the GitHub page of the core. So if you write on Google Open Hardware Group CVE32E40P, you will find the core repository. From there, you have a pointer to the documentation. You will see them, and they are basically all the extensions that improve the performance and code size density for data analytics, pattern recognition algorithms. So DSP extensions are hardware loop, MAC operations, SIMD extensions of vectorial additions, dot products, bit manipulations that are custom, not the one from RISC-V, as they have been developed years ahead. Load and store operations with auto increments of the pointers, and all these extensions that are actually meant to increase the performance, but still in a low power domain. So the area and powers are kept at the minimum.
Davide, maybe I'll jump in here just on the extensions discussion. Could you add a flavor around, as you said, some of the original PULP custom extensions were developed because the RISC-V Foundation hadn't completed in the ISA extension work, bit manipulation as an example. And from a roadmap standpoint, can you just comment on what we were intending to keep, if you will, in the PULP extensions, and how the core will evolve to implement the approved standard versions of some of those extensions?
Okay, so thanks, Rick, for the questions. If we are talking specifically about the CVE3240P core, the extensions based on PULP, which is the reason why of the P on the name, will stay there as they are and won't change. But if we talk about the family of E4 CV4s, so the next generation of this IP, the roadmap of the Cordas group is actually becoming more and more compliant with RISC-V. So as soon as, for instance, I mentioned the bit manipulation before, the bit manipulation today implemented in the CV32 core are based on the PULP one. But once they have the RISC-V one, so the official one, get ratified and standardized, the idea is to replace the custom extensions with the new ones. So and same for the DSP extensions and the SIMD extensions. They are today they are a draft under RISC-V under the RVP extensions, namely. But once they get ratified, we want to make the core RISC-V compliant also from the side of extension. So the idea is be as compliant as possible whenever the drafts are stable.
Right, very good.